Today, we're going to begin the other half of this unit, which is logarithms. Now, the very first and probably most important thing that you need to know about what a logarithm really is, it is literally just the inverse of an exponential function. So previously, we learned that the formula y equals a to the x is an exponential function. So you've got a base raised to the x power, and that's equal to y. So remember, and by the way, exponential functions do pass both the vertical and horizontal line tests, so they are one-to-one functions, so you can take their inverse. And when you take the inverse of an exponential, what you literally get when you switch the x and y in the formula is this formula, x equals a to the y. This is technically the formula for what a logarithm is. Now the problem is that mathematicians don't like their equations solved for x. If you think about it, every single other equation that we've ever seen and used and graphed has always been solved for y. So it bothered mathematicians for a very long time that they couldn't figure out how to get this formula solved for y. So this guy named John Napier came along in 1451 and invented something called a logarithm. He said, okay, you want to get the y on one side of the equation by itself? He goes, I'll do that for you. Here you go. Y is going to be on the left-hand side of the equation. To let people know that he was doing this, he was the first one to use the word logarithm. The base of the exponential becomes the base of your logarithm, and the answer to that a to the y power goes next to your logarithm. So one of the first things that we have to understand is when we're working with John Napier's form of logarithms, it's like, where does everything go? What part of that is really the exponent, the y? What part of that was the base of the exponential, the a? And the x that's next to the logarithm is really what used to be the answer to that problem. So in order to be able to work with logarithms, you need to be able to go back and forth between the exponential form of writing logarithms and the logarithmic form of writing logarithms. So let's practice with this a little bit. I've got some examples that are starting out in exponential form that we're going to take to logarithmic form, and then I've got some that are in logarithmic form that I want to bring back to exponential form. So the first one is 3 squared is 9, which I think we'll all agree is true. That's an exponential form. If you want to write that as a logarithm, you would put the base of the exponent as the base of your logarithm. So log base 3. The answer to the problem goes next to your log. So that would be log base 3 of 9. And the exponent in this would become the thing that goes on the other side of the equation. So in log form, the answer, the thing that's on the other side, is always the exponent from the exponential form. All right, let's try going from logarithmic form back to exponential form. So the base of your exponential, the base of your logarithm is the base of your exponential, so 5. And 125 is the answer that goes on the other side. And the thing that's on the side by itself is the exponent. So basically, if you want to take x equals log base 5 of 125 and write it as an exponential, it's 5 raised to the x equals 125. In this form, it would be very easy for you to figure out what x would need to be. If x was 2, 5 would only be squared. That's too small. X would need to be 3 in this problem. 5 cubed is 125, so we now know x is going to be 3 in that problem. Okay, let's practice one more time, going from exponential form to log form. So my exponent is 5. That's going to be on the side by itself. The logarithm is going to have a base of 10 because that's the base of the exponential. And the answer was x, so that's going to go next to my log base 10. Last example, going from logarithmic form back to exponential form. My base is 3. My exponent is -4. And the answer to this question is going to be 1 over 81 because the answer always goes next to the log and the exponent goes on the other side of the logarithm. Okay, we're going to learn about 2 special kinds of bases right now. Whenever we're doing log base 10, that's what's called common log. And this is the only logarithm that you won't actually see them write the logarithm for, the logarithmic base for. So on your calculator, that's just going to be LOG. So there's an LOG button. They don't put any little base next to the log, so that means it's base 10. So that's called common log. If you're doing a logarithm and your base is e, that's what they call natural log. And on your calculator, the abbreviation for that is going to be ln, because these were invented by that French guy, Euler, log de naturel. So that's why the L's in front of the N, if you were wondering. And we have a button for that on the calculator as well. The next thing that we're going to take a look at are some of the basic properties of logarithms. And what I mean by basic properties of logarithms are these are things that should work no matter what base logarithm that you want to use, whether you want to use base 2 or base 10 or base e or base 57, whatever. So the first one is log of any base a of 1 has to be 0. Now the reason for this, if you think about putting it back into exponential form, what are you really saying? You're saying your base of a, when raised to the 0th power, is going to be equal to 1. And that's going to be true no matter what your base was, whether you write it as a log or as an exponential. So we would be totally comfortable writing this in exponential form and understanding that's got to be true. Now what I'm telling you is you should know it when you see it as a logarithm as well. Our next basic property of logarithms is that log base a of a should always be 1. In other words, if you take a base of a and stick an exponent of 1 on it, you should get an answer of a. In other words, anything raised to the first power is itself. We would totally get it if we wrote it as an exponential. Now we have to be able to recognize it when we see it as a logarithm. And the last one of these basic properties for logarithms is that log base a of a raised to the x has to be x, because of course, if you take a base of a and you raise it to your x power, that's going to have to be equal to the answer that's next to your logarithm, which is a to the x. So in other words, a to the x power is equal to a to the x power, which of course is the same thing on both sides, so therefore they have to be equal. All right, so let's try a couple of quick examples of using the basic properties of logarithms. Log base 17 of 1. Well, log base 17 of 1 is going to have to be 0. Why? Because 17 is my base, and I'm asking you what exponent can I put on it to make an answer of 1. Well, remember, with logarithms, the thing that goes on the side by itself is the exponent, so it would need to have an exponent of 0. Okay, number 2, log base 5 of 5 raised to the 2x plus 3 power. They're giving me a base of 5, and they're asking me what is the exponent I could put on it that would make 5 to the 2x plus 3 power. The answer to this one is simply 2x plus 3. The thing that goes on the right-hand side of a logarithm is the missing exponent that you need to put on your base. A lot of people do it like this. They would just say that a logarithm with a base of 5 cancels an exponential with a base of 5. So you're just left with whatever the exponent is. And the last one, log base 23 of 23, is obviously going to have to be 1, because what you're really saying is, what's the exponent I'd have to put on 23 to make an answer of 23? Well, you'd have to put the first power on there. So that's remembering that logarithms are really just about finding your exponent. That's what they're actually solving for. Okay, the next thing that we're going to take a look at today are what are called the rules of expansion and contraction. These look all fancy, but pretty soon you're going to realize they actually come from rules that you're already very well aware of. The first one is the rule for doing log base a of u times v. The rule for doing log base a of u times v is the log base a of u plus the log base a of v. And the log base a of u divided by v is going to be the log base a of u minus the log base a of v. And the final one is log base a of u raised to the n power is equal to n times the log base a of u. If you use these rules going from left to right, that's called expansion. You're taking a single logarithm and you're spreading it out into multiple logarithms, or you're using the rule about exponents to bring the exponent out in front. So that's what we call expansion, turning one logarithm into many. If you're using these rules from right to left, you'd be taking multiple logarithms and squeezing them back together to make a single logarithm. That's what's called contraction. So these are called the rules of expansion and contraction, and which one of those things it is, whether it's expansion or contraction, depends on which way you're taking the formula. It's equivalent in either direction, but are you trying to turn it into many logarithms, or are you trying to condense it down into a single logarithm? So that's the difference. So the next thing I want to talk about really quickly is, where do these rules come from? So if you remember, the objective of a logarithm is to find the exponent. So when you say log base a of u times v, you're asking what is the exponent that I would need to put on a to make a product of u times v. So basically what we're doing on the right-hand side, if you think about it, we're using the same base, log base a, and what we're doing is we're adding together the exponents that you would have gotten from log base a of u and the log base a of v. So in other words, this is actually our first rule from working with exponents. If you're multiplying together powers that share the same base, you should add their exponents. Remember, log base a of u is the exponent, and log base a of v is an exponent. And if you add those two exponents together, you would get the result of log base a of u times v, which is the product. Similarly, when you do division, this is going to lead to subtraction, because what you're trying to do here is you're trying to subtract the exponents, log base a of u minus the log base a of v. So if you go back to our rules for exponentials, the first one is rule 1, what to do when you're multiplying together powers of the same base. The second one, division, is rule 2. And the last one, this one's interesting, the last one we oftentimes use when we're solving problems that have logarithms in there. What we're doing is, if you're doing a logarithm with a base of a, you already have an exponential going, a is your base, and then we have something inside of it that's being raised to another power. So basically, when you have a power being raised to a power, you need to multiply those two exponents together. So n is an exponent, and log base a of u is an exponent, and that rule about raising a power to another power says keep the same base and multiply the exponents. All right, so now let's use all of this. In the first two examples here, I'm going to do expansion. So I have log base 2 of 5 times x. I'm going to use the rule for expansion to spread this out into multiple logarithms. One of the key things to notice is that all of the logarithms will share the same base as the original. So because our original was log base 2, all of these are going to be log base 2. One of them will be on log base 2 of 5, and the other one will be on log base 2 of x. And because these terms are being multiplied, that means I'd want to add their exponents together, so put an addition in the middle. For example number 2, again, we're going to be trying to do expansion. So I'm trying to spread this single logarithm out into multiple logarithms. So I'm actually going to have, because I have a 3 and an x and a y that has a square root over the top of it, that's 3 different pieces to what's inside the logarithm. That means by the time I expand this out, there's going to be 3 different logarithms out here. Now, let's talk about each one together. We have log base 3 of 3 times x. 3 and the x are getting multiplied together. So I would do log base 3 of 3 added with log base 3 of x. That addition is coming from that multiplication that's happening in between the 3 and the x. Then we see that there's y's that are getting divided. So out here we're going to have a y and we're going to have a minus in front of it. And the last thing that I'll remind you of is that a square root is really a 1/2 power. And the third rule says when you're taking a logarithm of something that has its own power, you want to drop that exponent down out in front of the logarithm. So this one would have a 1/2 out in front of the log base 3 of y. That 1/2 would have been the exponent that was on the y, which is a square root basically. All right, for the last one, we're going to be going the other way. This one is starting with multiple logarithms, and I'm going to try to do some contraction. In other words, I'm going to squeeze this all back together into one logarithm. As long as the logs all share the same base, which they do, they're both log base 2s, I should be able to turn this into one logarithm with a base of 2. Now, it probably will help if you'll put parentheses here. Remember that any numbers that are out in front of the logarithms, those are exponents on the things that were inside. So basically, I've got an x cubed that was inside of this logarithm, and I have a 2 that's going to become the exponent on the y, and I see that there's a subtraction in the middle, which means there was division occurring. So the x cubed was on top, and on bottom we're going to have a y squared because the 2 was the exponent on y. So we put the numbers that are out in front back into their exponential place, and we look in between to see if it was being added or subtracted. Subtraction means division. So log base 2 of x cubed over y squared. All right, on our last page of notes, we're going to learn about something called the change of base formula. Now, you may or may not have seen this. If you have an older calculator, you do not have a button for taking a logarithm of any base, so you would have to be able to use this and know what it is. But if you have one of those newer calculators, you probably can take the logarithm of any base that you want to. Let me show you what the formula is. The formula says if you're going to take log base a of b, that would be equal to the common log of b divided by the common log of a, or you could do natural log of b divided by the natural log of a, either one of those. And the reason why they always use the change of base formula with common log or natural log is because those are buttons that all calculators will have. So what can be done with the newer calculators, though, is if you go into the math menu, if I hit the math button, and I go over to, which one is it now? I think it's in math. Yeah. Oh, it's in the math button. If you go all the way down to choice A, it'll say log base. Now, when you choose that, it'll show log, and there'll be a little box down here, and then a bigger box up here, so you could fill in whatever you want for a base and whatever you want for the answer behind it. But if you don't have the newer calculators, you won't have that. So let's just take a look at a couple of examples. I'll show you how to do it on the calculator both ways. And then what I want to get is I want to be able to get you to the point where you can predict what the answer is going to be. So the first one we're going to do is log base 2 of 100. If you have an older calculator, you'd want to do the change of base formula and do something like common log of 100 over common log of 2. Now, when you're doing this, you'd have to close the parentheses off on the logarithms on the calculator before you do each one before the division. But before I actually type this into the calculator, I want to see if you guys can predict what you're going to get as a result. Remember, the answer to a logarithm is the exponent. So basically what I'm asking you is, what exponent would I have to put on 2 to make an answer of 100? Well, we know that 2 squared is 4, and 2 cubed is 8, and 2 to the 5th power is 32, and 2 to the 6th power is 64. 2 to the 7th power is going to be 128. So the answer that I'm looking for is somewhere in between 6 and 7, because 2 to the 6th is too small and 2 to the 7th is too big. So now when I actually do this on the calculator and I take the common log of 100 and divide it by the common log of 2, I will find out the exact answer for this is 6.64385619. And that's exactly where I was expecting that answer to come out, somewhere in between 6 and 7, because what we're really looking for is that's the exponent that you could put right here to make this sentence work out to be true. So let's try one more. Log base 5 of 37. So again, as a predictive tool, what I'm really making sure that you understand in this unit is I'm asking you for the exponent that we could put on a base of 5 that would make an answer of 37. And right away, I hope that everybody knows that the answer for this has to be between 2 and 3, because 5 squared is 25 and that's too small. 5 cubed is 125 and that's way too big. So if I had to guess, this answer is in between 2 and 3, much closer to 2. It's probably 2 point something, just a little bit. So if you want to do the change of base formula, you would take the common log of 37 and divide it by the common log of 5. Or you could use natural log of 37 and divide it by the natural log of 5. Either way, it would produce the same answer. And let's see what that does turn out to be. 2.2435 89445. And that's exactly where I was expecting that answer to be, somewhere in between 2 and 3, closer to 2. Okay, so use this to help you with the homework that I've assigned tonight.